But I'm going to tell you first a little bit about the Lucy mission. And of course, every project that we do is a lot of people. This is the science team, not even the whole science team, at the launch in October 2021. But the science team is only a small part of the much larger team of engineers and many other people that support an enterprise like this. So it makes it very fun. We have a great group. I love our team. So that's what makes it really fun to get up and work every single day. So what about the Lucy mission? A lot of NASA missions get their names from acronyms. Ours is not an acronym. It was just named after the Lucy fossil, which was found in 1974 in Ethiopia by Donaldjohanson, this handsome guy in the lower right corner of the screen. And they, the reason we chose that name was because we think that the Trojan asteroids, which I'll explain in a minute what they are captured at the end of a very early and chaotic part of the solar system. And they're the lucky survivals, the lucky survivors who have been kept in these stable orbits for the last 4 billion years or more. And they're one of the few populations in the solar system that we haven't visited yet with a spacecraft. So this is what the Trojans are. If you were to look at a map of the solar system, the sun's in the middle, then there's Mercury, Venus is the white one, Earth is blue, Mars is red, and Jupiter is this farther out one that's orange. Now, most asteroids, I don't know if you can see my cursor, whoops, orbit between Mars and Jupiter. But these two groups are stuck at Jupiter's distance from the sun, but they are always either ahead of Jupiter or behind. And that's because they're at these dynamically stable points called Lagrange points. And specifically, they're the L4 and L5 Lagrange points. So they're sort of like the fly paper sticky trap that has kept those asteroids in place since the beginning of the solar system when the early chaotic phase came to an end. And that's what we want to go visit them. Here's a diagram that shows a cartoon of the objects that we're going to go to. And this is going to be over the course of the mission. So we get to our first Trojan target in August of 2027. It's really only a little more than 2 years from now, so it's coming up fast. We'll see 4 of them over 14 months, and then we dip back, go past the Earth again, and then fly by the last 2, Patroclus and Menetius, in March of 2033. And just to give you an idea of the sizes here, the largest ones are about 100 kilometers across, that's like 60 miles. And the smallest one, this little satellite of Euripides that we've named Keta, is about half a mile across, a kilometer or so. So there's a big range, and for an asteroid, 100 kilometers is big. So these are some of the largest asteroids, all the way down to sort of average, typical asteroids to the smaller ones. So we're going to see many different kinds of asteroids, and that allows us to do some interesting science. On our spacecraft, we have a bunch of science instruments. We have cameras. We have a wide camera that's called TT cam. We have a high resolution camera that we call LORRI. We do science with the radio antenna to allow us to measure the masses of the objects. We have an instrument called LRALPH that is used to measure composition. And then we have another instrument called LTEST that measures temperatures. So we get a really good handle on these objects with many different dimensions of measurements during the flybys. All of our missions are flybys. All of our encounters are flybys. So they happen very quickly, and you'll get a sense of that in a movie that I'm going to show you. So we have to be prepared well in advance with all of our observations planned out and computerized on the spacecraft. So in order to make sure that we know how to do that right, we actually had already planned to do a test encounter with the asteroid that we just passed, Donaldjohanson. But in late 2022, a colleague of ours, Raphael Marchal, identified another tiny asteroid that we hadn't even really thought about, asteroids that small, that we had a chance encounter with. So this is turns out to be the first asteroid that we went by, and it was a great test of our systems because it was so small. It really showed us how well our systems work, and it had a few surprises for us. So this little movie just shows Lucy coming up. This is after the first Earth gravity assist. We have had two of those now. We need those to boost us out to Jupiter's orbit. The first boost only got us out just barely to the main asteroid belt, which is only a little bit past Mars. But as you can see, we get out and we have that very close encounter with Dinkinesh. And where'd that name come from? Well, Raphael, or we chose the name Dinkinesh once we realized that we were going to fly by. And Dinkinesh is the name that for the fossil, the Lucy fossil in Ethiopia. So it means you are marvelous in Amharic, which is one of the languages in Ethiopia. And we thought that was an appropriate name for this asteroid, which before that just had a number 152830. So we have to give our targets a little bit more personality by giving them names. Well, when we selected this, we knew very, very little about it. We knew that it was orbiting on the inner edge of the main asteroid belt. There's a map here that you can see that gives you an idea of how far out the main asteroid belt extends. So here's the inner edge, and out here's the outer edge, and there's all this detail in here that is a fascinating topic of its own, but I don't have time to get into it. But one of the first things that we did then was measure the spectrum. And from this spectrum, we can tell roughly the composition of this. It turns out to be a rocky asteroid. And because we've seen so many of these, we have a rough idea of how much light that asteroids like that reflect. And we can use that to estimate the size of the object. At first, we were concerned because we thought it might be too small for our systems to work. It turned out that it was just barely big enough, and our estimate was 700 meters in diameter, which was very close to what it actually turned out to be. But to give you another idea of the size of this thing, I've got two groupings here. The upper grouping is asteroids in the main belt that have had spacecraft fly by them. And some of them are better imaged than the others. You can see some of the images were kind of fuzzy because the spacecraft didn't get too close. And Dinkinesh, our estimate of the size was this less than a kilometer, 700 meters over here, which would make it the smallest asteroid in the main belt ever to be visited by a spacecraft. And that turned out to be true. But we've also had spacecraft go to asteroids that come much closer to Earth. These are called near-Earth asteroids. They started out in the main belt and somehow got knocked out, and now their orbits come very close to the Earth. But some of those are objects we want to keep our eye on because we don't want them to hit the Earth. Those tend to be much smaller. And so Dinkinesh turns out to be a fairly average size compared to the other near-Earth asteroids that we visited. So we get a great ability now to compare and contrast how much the environment of these things affects what they end up looking like. So we've got an object in the main belt that's the same size as all these near-Earth asteroids that we see. It provides us a kind of a missing link between these two populations. All right, this is just a geometry diagram to prepare you for what you're going to see in the movie. So here's Lucy coming in. We're flying past Dinkinesh here. The sun is up here. So we come in sort of slightly on the night side, but we're coming in like at a half moon phase and a little bit less than a half moon, and we go out at a little bit more than a half moon. So that's what you're going to see. And it'll look like Dinkinesh is spinning, but that's just the spacecraft flying by and changing perspective. And the fact that we kept it in our cameras the whole way is the thing that we wanted to test the most with this. So I'll show you how well that worked. So there it is. We're approaching. This is probably a day or so out, and actually probably only a couple hours out. And now you can see we're getting into the last 10 minutes or so. And here we come. Last couple of minutes, we fly by. and then we head out on the other side. And let's show you that again. So at the closest, we came at about 500 kilometers away, so 300 miles away from it. And it's only about 700 meters across, so you get an idea of how strong our our telescopic camera is. It can bring out a lot of detail in the asteroid as we fly by. And it's really fascinating, all the structure that we see in that, because these small objects are what we call rubble piles. They've been beat up and bashed many times by collisions throughout the age of the solar system. This object in this state's probably only 10 million years old or so, which is young compared to 4.5 billion. But it has all this structure, and the structure is a clue to how it got to be this way. And the weirdest thing about it is this satellite. So the satellite is a contact binary. It's two lobes that are touching each other. And we've never seen anything like that before as a satellite. We've seen some uh, asteroids like that flying on their own, but never a satellite. So that's a real puzzle, how you can make something like that. And one of the more interesting problems that scientists are still working on today. And uh, Raphael Marshall, who found this for us, named it. He found what I think is the perfect name. Selam is the name of a fossil that is a baby of the same species as the Lucy fossil, and it means peace in Ethiopian. So it was a great name. We really like that. So what have we learned about this thing? Well, one of the things that you notice right away is that Dinkinesh has a top shape. We see this in many of the small, fast spinning asteroids. And in that image, the collection of near-Earth asteroids I showed you, there are a couple of those. And they get this shape because as they spin fast, the material flows from the poles towards the equator. And uh, the forces that are involved in that can have some interesting consequences. So in fact, we were able to measure Dinkinesh's spin, and you can see this looking from the top down. Dinkinesh is the main body spinning pretty fast in the middle, and then you see Selam, the satellite, moving around from the outside. This is just a simulation of what it would look like if you had this viewpoint. And compared to other asteroids, if you look over here in this chart, Dinkinesh is spinning pretty fast. In fact, as you go faster is going down, you pretty soon see that there are no objects spinning faster than about 2 hours, 2.5 hours. And the reason for that is that if they spin that fast, they break apart. So Dinkinesh is close to spinning as fast as it can. And if you put the satellite back together with the main body, so sort of like a ice skater pulling in her arms, it would be spinning at about that speed. So that is a very strong clue as to how this system ended up like it is. We can look at the geology and we see a couple of really prominent things. One is that on the equator of Dinkinesh, there's this big ridge. You can see this thing bumping out. This is three different views of it as we flew by. And you see this ridge here. And if you were standing on there, it would just be like a mound of dirt uh, all around the equator. How do you get that? Well, the other thing that's really prominent is there's a crack or a trough that goes all the way around uh, the asteroid from both sides. You can see this on both sides. It doesn't go, it's overlain by the uh, equatorial ridge, though. That means that this trough must be older than this ridge. But how much older, we don't know, maybe just a little bit. And in fact, what we think happened is that as Dinkinesh was spinning faster and faster, and this is one of these fascinating things that happen with tiny asteroids, they can be spun up just by solar radiation pressure. That only happens if they're smaller than a few kilometers in size. This one is. Bigger asteroids are too massive for that effect to have a big impact, but these small ones end up spinning fast just from absorbing and re-emitting sunlight. And eventually it was spinning, we think, so fast that it started to break apart. And you can see this little animation looks like, if you ever played around with the globe and noticed that Africa and South America fit together like puzzle pieces. That's what this looks like is going on here. And we think that what happened is that it was spinning fast. It started to come apart. It lost a lot of mass that went into orbit around it, and that slowed the spin down enough so that it didn't come all the way apart. And then the mass that was ejected in this big landslide, and it was now in orbit, forms a ring. Some of that ring rains down onto the equator and forms the ridge, and the rest of it forms the satellite. So we believe that is the history of how Dinkinesh got to be the way it is. And we see this played out in other environments in the near Earth environment. It looks like it's a fairly universal process. And in fact, small asteroids like this may go through many generations of spinning up, breaking apart, having a satellite, eventually losing the satellite, and then being spun up again. So this is important to understand in a way because it's these small ones, because there are so many, that we have to worry about when it comes to impacting the Earth. And in fact, Dinkinesh looks very much like another small near-Earth asteroid, Didymos, that was the target for the DART spacecraft that was testing the ability to deflect an asteroid that might at some future time come and hit the Earth. So now we're going to move on to Donaldjohanson just briefly. So there's the spacecraft. There's the first Earth gravity assist. There's the Dinkinesh flyby. And here we go. And we just, now we're heading out into the main Trojans. But on the way, we passed Donaldjohanson. I'll let this finish. You can see we go past 1, 2, 3, 4 in this cloud, the one that leads Jupiter, the L4 cloud. Then we go back and we get another Earth gravity assist. And then we come out and we have the encounter with the large binary in the L5 cloud in 2033. And that's the end of the mission. So that's what we're doing. But for now, let's go see what we saw at our second main asteroid belt test object, Donaldjohanson. So here's the flyby sequence, the close flyby sequence of Donaldjohanson. And I'll just let this play while I talk about it a little bit. So one thing that turned out is it was a lot bigger than we thought. So we had guessed that it was about half the size that it turned out to be because we're using an incorrect value for the how much light it reflects. It's darker than we thought, so that means it has to be bigger. And if you just look, you can see all kinds of fascinating detail on this thing. There's a lot of craters, obviously, many more than you saw in Dinkinesh. There are boulders on the surface. There are some interesting, weird-looking objects. The sun is off to the left in this image. And in case this is giving you vertigo, I'll just go to the still picture and walk around with my so you see these ridges here, and the general structure of this thing is there's a lobe here, the head, there's another lobe here, the body, and then there's this long neck. And it really looks like this was two separate objects that came together to form a single object. And in fact, when we look at other objects that are like this that spacecraft have encountered, we see that this pattern is fairly common. Here are all the contact binary objects that we know about in the main belt that spacecraft have visited. And we know about many more from radar images, from light curves, even some large objects in the main belt from ground-based telescopes. But these are the best collection of similar sized objects. These are all to scale here. So you can see that Donaldjohanson fits right in with this family portrait. Some of these are comets. Some of these are asteroids. The big one here, Arakoth, is in the Kuiper Belt. But it seems that the universe is trying to tell us something, and it's something that we don't completely understand yet, why this particular architecture is so common. We have some ideas. But like with Dinkinesh, Donaldjohanson gives us a great test because it's in the main belt. All these other things are either near-Earth asteroids or comets. And with both of those populations, since they are short-lived, you don't know how permanent or how primordial this kind of structure is. But with Donaldjohanson in the main belt, we know that this is at least 150 million years old. And we know that because it's part of a collisional family that formed at that time, 150 million years ago. So this is one of the directions that we're going to want to go with research, besides uh, detailing all of the other interesting features on the surface. And we haven't even gotten a chance to start working on the spectral data. We'll be looking for fresh craters, compositional clues, things like that. And it's going to be an exciting year or two of work on this data. So I think that's the end of my slides, but I'd be delighted to take some questions.